Researchers at CU Boulder have for the first time used X-ray computed tomography, also known as a CT scan, to peer inside swarms of honeybees. A honeybee swarm is a cluster made up of a queen bee and thousands of workers that hangs outside for hours to days while the workers scout for hives. Swarming is a precarious step in the life of a honeybee colony. If the queen or too many of the worker bees do not make it to their new hive, the entire colony will be lost. Bees attach to one another to support the weight of the entire swarm and keep the colony cohesive. Hence, the mechanical stability of these swarms plays an important role in the survival of the colony. The CT scans provide a deeper look at these humble insects. Bees, the group discovered, don't clump together in a random group. Instead, they seem to form dome-shaped structures following surprisingly sophisticated mathematical rules, or what researchers call a scaling law. The results could one day help engineers design more resilient buildings or even swarms of tiny robots that behave a lot like insects, said study senior author Peleg. And bees can achieve all this despite having brains the size of grains of sand. The group published their results in the journal Scientific Reports. Getting bees to sit still for their X-rays took some work. First, the researchers relied on honeybee queens to coax thousands of worker bees to join into swarms in the lab. These structures, which often hang upside down, look a bit like a wriggly jello mold. Then the team rotated those swarms in front of a small CT machine originally developed for veterinary hospitals. The effort was a success. The group's method is so precise, you can pick out individual bees in the 3D scans. The images could give scientists a new tool for understanding how bees and other social insects create such shape-shifting superorganisms. Peleg explained that when honeybee hives become too crowded, bee queens will fly away to search for another place to live. The queens bring thousands of worker bees with them, which will occasionally cluster around the queen to keep her safe, a buzzing, undulating security detail. They are also really flexible. In a previous study, for example, Peleg and her colleagues shook swarms of bees to try to mimic the force of a gust of a wind. In response, the bees flattened out into a pancake shape, helping them stay stable amid the tumult. The team wanted to peek inside a swarm and see what is happening. To do that, the group scanned 11 swarms of bees containing anywhere from 4,000 to 10,000 insects. Based on the researchers' calculations, a bee swarm works a bit like a cheerleading pyramid. More bees cluster around the base of the swarm, then thin out the further up they get. Bees also seem to arrange themselves so that no one layer has to carry more than its fair share of weight. In mathematical terms, the structure follows a scaling law in which each layer supports a weight that equals roughly its own weight to the 1.5 power. What this scaling law means is that each layer winds up using the same amount of its available strength as every other layer. In the same study, the researchers tested bees to calculate just how much weight a single honeybee could carry. A bee, it turns out, can lift about 35 other bees on average. Bees in a swarm, in contrast, only lift a maximum of about 4 other bees. Scaling laws like the one the team discovered are common in nature. Among human weightlifters, for example, how many dumbbells you can lift tends to vary based on how much you weigh, a relationship that follows a surprisingly consistent mathematical formula. The same kind of laws seemingly applied to bees. The researchers say that the existence of this scaling law hints that there might be general principles of organization for structures like these that we don't know about yet.